welcome back everybody. Here is the second part of our lesson on the first derivative test. And here's another function. We'll find the critical points and the intervals on which the function is increasing or decreasing. And we'll use the first derivative test to determine whether each critical point is a local minimum or maximum or neither. So here we have a rational function, and we need to start by finding its derivative. So we're going to use the quotient rule. Most likely you're going to use the quotient rule. So we have the bottom, x squared minus 3 times the derivative of the top, 3x squared, minus the top, x cubed, times the derivative of the bottom, 2x, over the bottom squared, x squared minus 3, quantity squared. Okay, now we need to get this to a point where we can figure out where it's equal to 0 or does not exist. So I'm going to simplify the numerator quite a bit, starting with distributing. So if we distribute the 3x squared, we have 3x to the fourth minus 9x squared, and then multiply these two together and we have minus 2x to the fourth. And that's over x squared minus 3, x squared minus 3 quantity squared. Now let's combine the like terms in the numerator, and we have x to the fourth minus 9x squared over x squared minus 3 quantity squared. Sorry, I wish my tool was a little bit better and my writing could be a little more clear. Now, if we want to find out where the derivative equals 0, we should set the numerator equal to 0. If we want to find out where the derivative does not exist, we should set the denominator equal to 0. We want both, so we're going to do both of those. So let's set the numerator equal to 0. How about if we factor an x squared out of both terms? So we have x squared times the quantity x squared minus 9 equals 0. Set each factor equal to 0, so x squared equals 0, and x squared minus 9 equals 0. For the first one, you're just going to get x equals 0, and for the second one, you're going to get x equals plus or minus 3. So at this point, we have 3 critical points. Now we're going to set the denominator equal to 0 as well. So x squared minus 3 equals 0. Add 3 to both sides, x squared equals 3, and square root both sides, and x equals plus or minus the square root of 3. So we have 5 critical points. We have 0, we have plus or minus 3, and we have plus or minus square root 3. Remember, what we're going to do with those critical points is we're going to use them to divide the number line into intervals, and then we're going to test the intervals to see whether the function is increasing or decreasing. Okay, so now it's time to make intervals. So we go from negative infinity to negative 3. That was the lowest of all those critical points. We go from negative 3 to negative square root 3. From negative square root 3 to 0. From 0 to square root 3. From square root 3 to 3. And from 3 to infinity. Okay, so we have 6 intervals when we have 5 critical points. Now pick a number in each interval. You don't have to say what number you pick. You can if you want to. Test it into the derivative and see if you get a positive or a negative. So let me remind you what the derivative was. The derivative was x to the fourth. Actually, it might be convenient if I write it in its factored form. So the numerator factors into x squared times x squared minus 9. And the denominator was x squared minus 3 quantity squared. Now back here, when I set the denominator equal to 0, I forgot about the fact that it was squared, but that's not going to change our results because you would just square root it, still have 0. And then you would add 3 to both sides. and then you would square root again. So we end up with the same thing. But sorry that I missed that step. Okay, back to where we are now. So we have our derivative, and let's take a number and plug it in the derivative. So suppose for the first interval, suppose we pick -5. So you're going to plug it into the derivative, and you don't really care what number you're getting, you just care if it's positive or negative, and it turns out to be positive. Then you move on to the second derivative, or the second interval, and you pick a number in there. Let's say you pick -2. You can't pick an endpoint, you have to pick something in between. So if you pick -2 and you plug it into the derivative, you end up with a negative. Then you move on to the next interval, you pick something in there. Let's say you pick -1, you plug it in the derivative and it's negative. Now you pick a number in the next interval, let's say you pick +1, you plug it into the derivative and it's negative. Next interval, you get a negative. Next interval, you get a positive. So what does that tell us about f of x? That tells us f of x goes from decreasing to, oops, sorry. Let me start that over. F of x goes from increasing to decreasing to decreasing to decreasing to decreasing to increasing. What does that tell us about maxima and minima? Well, we have a sign change. F of x is going from increasing to decreasing, so that tells us at x equals -3, we have a local max. Remember, a mix. We have a local max. Remember that increasing to decreasing means going up then going down, so it must be a max. And then we have another sign change. F goes from decreasing to increasing at x equals 3. So x equals 3 is going to be a local minimum. If you wanted to know the height of the minimum, you would find the y-coordinate of the point. Remember, going from decreasing to increasing means the graph is doing this and then it's doing this, so that's a minimum. And then the other points, they were critical points, but they didn't work out to be maxes or mins. And the problem also said that we should graph this on the calculator to verify. So I'm going to go ahead and take a look at what this looks like on my calculator, and then I'll come back and make a sketch. Okay, so this function has a vertical asymptote at -√3, it's about 1.7, and +√3. And then it's doing this. Okay, so we can see the local maximum here at x equals -3, the local minimum here at x equals +3, and we can see that we don't have any other local maxes or mins. Okay, now let's take a look at the next example. So this one involves an exponential function, and it's a product. So we're going to find the derivative using the product rule. So we have f prime of x equals the first, x squared, times the derivative of the second, e to the x, plus the second, e to the x, times the derivative of the first, 2x. Okay, this is defined everywhere, so we just need to figure out where it's equal to 0. And I'm going to write it as x squared, e to the x, plus 2x, e to the x, equals 0. In order to solve an equation like this, it's really, really handy if you can factor it. So notice that we can factor an x out of both terms, and we can factor an e to the x out of both terms. And that leaves us with x in the first term and 2 in the second term. Now think of this as 3 factors. The first factor is x, the second factor is e to the x, and the third factor is x plus 2. So set each factor equal to 0. We have x equals 0, so there's a critical point. We have e to the x equals 0. However, there are no solutions to that, because if you think about what the graph of e to the x looks like, it's always positive, it never equals 0. And then the third one, x plus 2 equals 0, so x equals -2. So we have 2 critical points. 0, and negative 2. So we can go ahead and make our intervals. We have the interval from negative infinity to negative 2, from negative 2 to 0, and from 0 to infinity. And now we want to pick a number in each interval and test it into the derivative and see if we get a positive or a negative. The place I would test it is into the factored form. And so let's pick a number between negative infinity and negative 2. Suppose we pick negative 3. So we're going to get a negative times a positive times a negative. So that's going to be positive. Now let's pick something in here. Let's say we pick negative 1. We're going to get a negative times a positive times a positive, and that's negative. Now let's pick something in here. Suppose we pick 1. We're going to get a positive times a positive times a positive, and that's positive. So what's happening to f? F is going from increasing to decreasing to increasing. Therefore, we do have a local maximum at x equals negative 2, and we do have a local minimum at x equals 0. So the method that I'm using to assert that conclusion is called the first derivative test. So you could say, according to the first derivative test, we have a local maximum at negative 2, a local minimum at 0, because the first derivative test just means you're going to see if you have a sign change in your derivative from positive to negative or negative to positive. Okay, so what I'm going to do next is figure out which homework problems I want you to do. I'll give you probably like 3 or 4 homework problems, and then I'll also make a solution video for you so that you can check your work. Thanks, everybody.